Hello everyone, so in this lecture we will study about the electric field. So what is electric field and what will be the value of electric field due to a point charge and electric field due to different continuous charge bodies, what are the electric field lines, what are their properties. So let's start from what is the electric field. So we have seen that suppose there is a positive charge plus q charge. If now we bring another charge near this charge, suppose there is a charge plus q naught, then there will be a force upon this q naught charge due to this positive charge, right? If we bring some other charge, then there will also be force on that charge due to this positive charge. That means there is something around this positive charge in surrounding space, and that is called electric field. And electric field is a vector quantity and is denoted by capital E, and it is written like E equals to F upon Q naught. Q naught is the value of test charge, and here F is force experienced by this test charge. Suppose if both are positive charge, then the force will be repulsive in nature and direction will be like this. So this force upon this Q naught test charge is called the electric field intensity due to this positive charge. And we take this test charge in a very small quantity so that the electric field intensity is not affected by this test charge. So we can write electric field is limit Q naught tends to 0 of F upon Q naught. So this is the electric field intensity defined for a point charge plus Q. This is the electric field intensity due to this plus Q charge, this plus Q point charge. Now we know the value of F. What be the value of F? K Q naught upon R square and upon Q naught. So this will be K into Q upon R square. This will be the electric field intensity due to plus Q charge at a distance R. That means electric field due to a point charge will be K into Q upon R square. Unit will be Newton per Coulomb. And we have to remember this formula. Dimension you can find from Newton and Coulomb. Now electric field is a vector quantity. So what will be the direction of electric field? So if this is the plus Q charge, right, and we bring some another charge, some test charge Q naught, and suppose this is also a positive charge, then the force on this charge will be in this direction, right? And we have seen E equals to F upon Q naught, right? Now force is in this direction and this charge is positive, then E will be also in this direction. And if we bring some another charge, some another positive charge, suppose Q1 here, then force will be in this direction, and the electric field intensity here also will be in this direction. That means electric field intensity will be radially outward for a positive charge. So for a positive charge, electric field intensity will be radially outward. and for a negative charge body it will be radially inward direction. Right. So relation between F and E will be F equals to Q into E. Remember this formula? We'll put Q with sign for direction. Right. So if we put a charge in a electric field, suppose this is the direction of electric field, if we put a charge plus Q charge, then there will be a force on this charge in direction of electric field. If we put another negative charge, then the force on this charge will be opposite to electric field direction. Right. It means the positive charge in an electric field will move in the direction of electric field, and the negative charge in an electric field will move in direction of opposite to the electric field. So first remember this formula, F equals to Q into E, and electric field due to a point charge at distance r equals to E equals to KQ upon R square, and direction of electric field is radially outward for the positive charge and for a negative charge radially inward. Now we will solve some question based on this formula. So the magnitude of electrostatic force experienced by a charge of 1 into 10 raised to power minus 6 coulomb is 1.5 into 10 raised to power minus 3 Newton. Find the magnitude of the electric field at the position of the charge. So what we have given, Q charge, value of charge we have given, and force we have given 1.5 into 10 raised to power minus 3 Newton. So the electric field will be F equals to Q into E, we know. So electric field will be F upon Q. Value of F is given 1.5 into 10 raised to power minus 3. Value of Q given 1 into 10 raised to power minus 6. So this will be 1.5 into 10 raised to power 3. Unit we know, Newton per coulomb. So this will be the value of electric field at the position of the charge. Now the other question is given a water droplet of a mass 10 milligram. So mass of the water droplet is 10 milligram and having a charge of 1.5 into 10 raised to power minus 6 coulomb. So value of Q is 1.5 into 10 raised to power minus 6 coulomb. Stays suspended in a room. What is the magnitude of electric field in the room and what is its direction? So what we have given, there is a water droplet and it is suspended in a room. That means there are two forces in opposite direction and they are equal. That's why the water droplet is suspended. So there will be a force on this water droplet, gravitational force, that will be in downward direction and that will be m into g, and this should be some force in upward direction and that will be the electric force over electrostatic force, and that is F equals to Q into E. So this is electrostatic force and this is gravitational force. That means these two forces should be equal for suspending the water droplet. So we can write m into z equals to q into e. What is the value of m? Value of m is 10 into 10 raised to power minus 3. This value is now ground, so we have to convert in kg. So 10 raised to power minus 3 also. Value of G is 10 given. Now Q. Value of Q also given 1.5 into 10 raised to power minus 6 coulomb. And value of E we have to find. Right. So value of E we can find from here. Now direction of electric field. So charge on this droplet is positive charge, 1.5 into 10 raised to power minus 6. That means the electric field will also be in the direction of force. So direction of electric field will be upward. Now the electric field due to many charges. How we find the electric field due to many charges? First we will calculate here. Suppose there are charges Q1, Q2, Q3, and we have to find electric field at some point P, and suppose this distance is R1 and this distance is R2 and this distance is R3. So what will be the electric field at P? It will be electric field due to Q1 in vector form plus electric field Q2 due to Q2 in vector form. Similarly, electric field due to charge Q3 in vector form. So we simply add electric field in vector form, right? This is the superposition of electric field intensities. Now in this question we are given two charges minus 10 coulomb and 10 microcoulomb. 10 microcoulomb and minus 10 microcoulomb are placed at point A and B separated by a distance 10 cm. Find the electric field at a point P on the perpendicular bisector of AB at a distance of 12 cm from its middle point. तो इस क्वेश्चन में थोड़ी सी कैलकुलेशन है. सो मैं आपको एक आइडिया देती हूँ कि इस टाइप के क्वेश्चन कैसे सोल्व किए जाते हैं. सो हियर इज 10 microcoulomb and here is minus 10 microcoulomb. And this distance is also given 10 centimeter. Now perpendicular bisector. Suppose this is the perpendicular bisector and this point is O, then AO बराबर OB and that equals to 5 centimeter. And this is the point P where we have to calculate electric field intensity, and it is at a distance of 12 centimeter from a midpoint of AB. That means distance OP is given 12 centimeter. So what we have to do? We will calculate the electric field due to 10 microcoulomb which is placed at point A. So this will be in this direction, and due to this charge, this is negative charge, so this will be towards the charge, so this will be in this direction. Magnitude of electric field will be same because the charges in magnitude are same and distance also same. So kq upon r square by kq upon r square, magnitude of electric field will be same. Now for the resultant electric field, we have to find this angle, right? Or the second method is we can resolve this electric field in two factors. If we know this angle is theta, suppose this angle is theta, then this angle will also be theta, and we can calculate this angle by tan theta. How? Tan theta equals to AO upon OP. AO is given 5, OP is given 12, right? So this theta will be tan inverse of 5 upon 12. So this component will be E cos theta, and this component will be E sin theta. Similarly, this angle will also be theta. So if we resolve this electric field in two components, then there will be component E sin theta and E cos theta will be in this direction. If we see E cos theta and E cos theta cancel each other, the total electric field will be 2 into E sin theta. Here E is K into Q, that is 10 into minus 10, 10 into 10 raised to power minus 6 coulomb upon R square. R is AP. AP we can calculate by Pythagoras theorem. If this is 5, this is 12, then this will be the 13 centimeter. Into sin theta. We know the value of tan theta, then we can calculate the sin theta also. So sin theta will be 5 by 13. So if we calculate this value, then we will find the total electric field due to these two charges at a point P, which is on perpendicular bisector of the AB. So this is how we simplify and calculate the electric field. Now we will see continuous charge distribution. So we will find the electric field due continuous charge bodies, and before that we will see what is the continuous charge distribution. So a continuous charge distribution system is a system in which the charge is uniformly distributed over the conductor, right? Over the conductor, and in this system infinite number of charges are closely packed and have a minor space between them, right? So continuous charge distribution में जो आपका चार्ज होता है वो यूनिफॉर्मली डिस्ट्रीब्यूट होता है, एंड द सेकेंड इज जो चार्ज पार्टिकल्स होते हैं, जो इन्फाइनाइट नंबर ऑफ चार्जेस होते हैं, वो क्लोजली पैक होते हैं. And this can be three types: linear charge distribution, surface charge distribution, and volume charge distribution. So linear charge density is defined by lambda, and suppose there is a road which length is L and total charge which is uniformly distributed on this road, that is Q, then linear charge density will be Q by L. Right? Q is the charge uniformly distributed over this road and L is the length of this road. Right? Now the surface charge distribution. Suppose there is a surface, suppose there is a sphere, and there is a charge distributed on surface of a sphere, then and that is uniformly distributed. Then the surface charge distribution, which is denoted by sigma, surface charge density, sigma is Q upon area of this sphere if the total charge is Q. There can be seat also. Suppose there is a seat which is uniformly charged, and the area of the sheet is A, and the total charge which is distributed uniformly on this sheet, then the surface charge density. Sigma will be Q upon A. Similarly, the volume charge distribution, suppose there is a sphere or a cylinder and the uniform charge distributed over the sphere uniformly, and suppose the total charge is Q and the volume of this sphere is V, then we can say the volume charge density is Q upon V. Right. Now units of sigma, units of lambda and units of rho will be given by coulomb per meter square and coulomb per meter cube. Because lambda is Q by L, sigma is Q by area and rho is Q by volume. Now we will see, we will do a question before going to electric field due to continuous charge, continuous charge bodies, right? So in this question we are given a uniformly charged conducting sphere of 2 meter diameter. This is diameter, has a surface charge density of 80 microcoulomb per meter square. Find the charge on the sphere. So we know sigma equals to Q upon A. Sigma equals to Q. Q we have to calculate. Value of sigma is given. So this is 80 into 10 raised to power minus 6 coulomb per meter square. Q we have to calculate. A is, this is the sphere. So what is the area of sphere? That is 4 pi r square, and value of r is 2 by 2 because diameter is 2, so 1 meter. So here we can calculate 4 pi into 80 into 10 raised to power minus 6 coulomb. We can simplify this and can calculate the charge on this sphere. Now electric field due to various continuous distribution of charge, how we calculate this? Suppose there is a body and this is uniformly charged and total charge is Q. Then what we do? We will take a very small element from this body and suppose the charge on this body is Q. Now this is like a point charge, right? Suppose the charge is dq, right? So due to this point charge, electric field at a distance r will be written like E equals to, suppose this is dE. dE equals to k into dq upon r square. What is the dE and what is the dq? This represents a small quantity. Now if we want to calculate the total electric field, then that will be the sum of the electric field by these small elements. So E will be the integration of dE, and that will be k upon r square integration of dq. Integration of dq will be total charge, right? So that is kq upon r square, and it will be kq upon r square when q is not related to r. Q is independent quantity. So this will be true for when the charge is not related to radius or not in the another form. So we can write the electric field for continuous charge bodies like this, and we can't remove k upon r square. Maybe the charge is in function of distance. So we can say the electric field for continuous charge distribution will be sum of electric field due to small elements. Now हम बहुत सारे डिफरेंट बॉडीज के कारण इलेक्ट्रिक फील्ड देखेंगे, बट वी विल नॉट derive the formulas. We will write the formulas and we will remember the formulas. So first, due to a point charge, we know due to a point charge, suppose there is a point charge q and at a distance, electric field will be written k q upon r square, and if we see the graph between E and R, that will be like this. So remember this formula and remember the graph also. So with the distance, the electric field intensity will decrease. Now due to a line charge, suppose there is a line charge and this is positively charged, suppose, and linear charge density is lambda. Length of this is L, and suppose there is a point P. So at P, what will be the electric field? First of all, there will be two components. Suppose one component in x direction and another in y direction. If we join the end of this line charge and if this angle is alpha and this angle is beta, then the electric field in x direction, it will be k lambda upon r sin alpha plus sin beta. And the electric field component of in y direction, that will be k lambda upon r. What is the r? R is the distance of point P from the line charge. This is r. This will be cos beta minus cos alpha. Now how to calculate direction? So Ex will be in this direction also, in this direction only for positive charge. For negative charge, it will reverse. And Ey will be calculated from this. If this is positive, then the electric field will be in this direction, and if it is negative, then the electric field direction will be opposite to this direction, right? So total electric field will be like this. So remember these two formulas. Now if this line charge is infinitely long due to a infinitely long charge, so if there is a line charge which is infinitely long, then the electric field at a point P, it will be Ex will be k lambda upon r sin alpha plus sin beta. What will the value of alpha? Is 90 degree. If we join the end of this infinitely long line charge, then angle will be 90 degree. So sin alpha is sin 90, sin 90 is 1 plus sin beta. Sin beta will be sin 90 degree, that is 1. So this will be 2k lambda upon r. Ey will be k lambda upon r sin beta, that means sin 90, that is 0. Correction, cos beta. Cos beta is cos 90, 0 minus cos alpha, 0. So this will be 0. That means E total will be 2k lambda upon r. Here we can say alpha, beta 90 degree. Right? So total electric field will be away from this infinitely long charge if the charge is positive, and if negative then it will be towards the charge. So remember this formula. Now before going circular ring, we will see electric field due to a line charge but semi-infinite, or we can say कि if we want to calculate the, suppose this is the line charge which is infinitely long, but we want to calculate at one end. What will be the value of beta? Beta was this angle. Beta will be 90 degree because this is infinitely long. What will be the value of alpha? Is 0 degree. So Ex will be k lambda upon r sin alpha plus sin beta, that means sin 90 degree plus sin 0 degree, that is 1. So k lambda upon r will be Ex, and Ey will be k lambda upon r sin beta. Sin beta is 90 degree, so 0 minus sin alpha, that is 1. This will be minus k lambda upon r. That means electric field at point E will be, Ex will be in this direction and Ey will be in this direction. Both components are same in magnitude. So total electric field will be in this direction at 45 degree angle, and this will be root 2 into k lambda upon r, because if two vectors in magnitude are same at 90 degree, then the resultant will be root 2 into magnitude of one vector. So the value of electric field, total electric field, will be root 2 k lambda upon r. Right. Now the third condition. Third condition we will see here. This is the infinitely long wire, but the point is here which makes the angle alpha from one end, but from the other end it makes angle beta, which is 90 degree. So simply we will put the values in formulas and we can calculate the electric field. Now the graph of electric field, this we are calculating due to wire line charge. With respect to distance r, values like in every equation there was k lambda upon r, right? So it is proportional k lambda upon r means it is proportional 1 upon r, so it will be hyperbola, and graph will be like this. With distance, electric field intensity will decrease. Now due to a circular ring, so suppose there is a circular ring, first we will remove this part. So वीडियो को पॉज करके आप इसे नोट कर सकते हैं. Now I'm removing this part. Okay. So now due to a circular ring, suppose there is a ring and this is placed like this, it is perpendicular the screen, not in the screen. So suppose the charge is uniformly distributed and the charge density is lambda and the total charge is q and the radius is capital R. So now at a distance r from the center, electric field will be kq upon x square, करेक्शन इसे और इसे x ही कंसिडर कर लेते हैं, एट वी विल confuse between r and small r and capital R. So this is the x distance at point P. X square plus r square power 3 by 2. This will be the electric field due to this ring, and it will be away from the ring if the charge is positive and towards the ring if the charge is negative. Now if we want to calculate at center, then x will be 0 and electric field will be k q upon x will be 0. So the electric field करेक्शन ये फॉर्मूला होगा के क्यू एक्स, यहाँ पर होगा x, सो के क्यू इंटू 0 अपॉन आर क्यू एंड दैट बिकम 0, राइट. सो remember this formula kqx upon x square plus r square the whole power 3 by 2. This is the electric field due to a circular, uniformly charged circular ring, and x is the distance from the center of the ring and at center electric field will be 0. Now if the distance x is greater than the r, greater than very large, then we can ignore the value of r and it will become kqx upon x cube and it will like kq upon x square, right. So for very large value of x we can write electric field kq upon x square. Another point to remember, at x equals to r by 2 and minus r by 2. What is the minus r by 2? Here also, in this direction also, at distance r by root 2, not r by 2, r by root 2. Value of electric field will be maximum, and that maximum value you can find by putting the r by root 2 in this formula. Now if we see the graph of this electric field, first of all we can say the electric field will be similar around the y-axis. So graph will be like this. Similarly in this direction also. And this distance will be x equals to r by root 2. This will be minus r by 2 and this will be plus r by root 2. Here will be the E maximum. Remember this graph also. आप लोग क्या करें, जो भी मैं फॉर्मूला बताती जा रही हूँ, जो इम्पोर्टेंट पॉइंट्स हैं उनके लिए आप एक अलग से नोटबुक बना लें और उसमें अलग से नोट करते जाएं चैप्टर वाइज. इससे क्या होगा, जब एग्जाम से 3-4 डेज पहले आप एक साथ रिवीजन कर सकते हैं, क्योंकि तब आप पूरे नोट्स लेके नहीं बैठेंगे कि क्या फॉर्मूला था या क्या पॉइंट था, तो वो बहुत टाइम कंज्यूमिंग हो जाएगा. सो आप फॉर्मूला की अलग सीट बना सकते हैं. Now due to a cylinder, suppose there is a cylinder which radius is capital R. And the charge density is lambda. So first of all we'll see ki what happens when the we give a charge to a conductor and we give a charge to non-conductor. So if we give some charge to a conductor, then it will accumulate on surface only, and if we give the charge to a non-conductor, then it will be uniformly distributed over the volume. Suppose there is a sphere and this is conductor, then the charge giving this sphere will accumulate on the surface only. Inside the sphere there will be no charge, and if this sphere is non-conductor, then the charge will accumulate in volume also. It will be uniformly distributed over the volume. So we will calculate the electric field for a cylinder due to a conductor cylinder and non-conductor cylinder also. So for a conductor cylinder, the charge will be uniformly distributed over the volume, and this is for non-conductor. Now for the conductor sphere, charge will be distributed on surface only. And the radius of the surface is capital R, which is very small compared to length of the cylinder. That's why we will treat it like a wire. So first case, outside the sphere. Outside the sphere, for a non-conductor, electric field will be K lambda upon r at a distance r. Distance are measured from the center line of the cylinder, and this is same for non-conductor and conductor cylinder, right? This is for both. And E at the surface, if the point P lie at the surface, then the electric field will be 2k lambda upon capital R, because the small r becomes a capital R. This distance is measured from the center line, so at surface it will become the capital R. Now inside, and this is also same for both. This is second case. Now the third. If point P lie in the inside the cylinder, so E inside will be k lambda r smaller upon r square. And this will be for non-conductor cylinder. For conductor cylinder, inside the cylinder electric field will be 0. So remember these formulas. Now if we see graph, so graph will be different for non-conductor and conductor. So if we draw the graph here, for non-conductor, 0 to r equal to 0 to capital R, that means inside the cylinder. Inside the cylinder, E directly proportional to R. So formula graph will be like this. This is the electric field and this is the R. At surface it will be 2k lambda upon capital R. After the surface it will like hyperbola. So maximum electric field will be at the surface, that will be 2k lambda upon capital R. This is the graph for non-conductor. For conductor, graph will start from surface because inside it is 0. So graph will start from surface and it will be like this. Now for due to a conducting sphere. So due to a conducting sphere, that means whatever the charge we give the sphere, it will accumulate on the surface. Suppose this is the sphere and the total charge is Q, then the charge will accumulate on the surface of this conducting sphere. Radius of this sphere is capital R. So we will study 3 cases: E outside, electric field outside the sphere at a distance R, at point P, it will be equals to kq upon r square. We can treat the sphere as a point charge for outside point. For inside, for the surface, electric field will be kq upon r square. For inside point, it will be 0. And it is same also for conducting cell also. Now, graph will be like this. Graph will start from surface and it will be like this. It will not hyperbola because the electric field is inversely proportional to the square of the distance, and this value will be the maximum and this value will be kq upon capital R square, where capital R is the radius of the sphere. Now if we calculate due to uniformly charged non-conducting sphere or non-conducting cell, so it will be like this. Charge density is rho, and this is total charge upon volume. Volume can be written 4 by 3 pi r is per pi r cube. So this will be 3q upon 4 pi r cube. All charge can be written 4 pi r cube into rho upon 3. Now, first case inside outside the sphere, we can assume the sphere as a point charge, and that will be kq upon r square. And distance are from the center of this sphere. Second case is surface. It will be kq upon capital R square. Third is inside the sphere, because inside the sphere now there will be some charge. So it will be like this. kq r upon r cube. So now if we change these formulas in terms of rho, then this will become case 1 upon 4 pi epsilon naught, q is 4 by 3 pi r cube into rho, and r square is here. So this will become 4 pi to 4 pi cancel, so this will become rho r cube upon 3 epsilon naught, and this will become simply and r square also, right? Simply put the r equals to capital R. So if we put, then it will become rho r upon 3 epsilon naught. And if we change this one, then this will become rho r upon this will become rho into capital R, rho r upon 3 epsilon naught. So electric field we can write like this. Now if you see graph, so graph of the electric field due to a non-conducting sphere. So till the surface it is proportional to distance, so it will be a straight line. After the surface, that means outside the sphere, it is inversely proportional to square of the distance, so it will become like this. Here will be the maximum electric field intensity, and that will be kq upon capital R square. Now if we remember these old formulas in terms of rho also. Now due to infinite charge non-conducting sheet, so suppose there is a sheet and that is infinitely long, and charge on this sheet is Q and charge density is sigma. Then the electric field from this sheet at distance r, it will be sigma upon 2 epsilon naught. And this is independent of the distance. So electric field will be same at every point. If you want to draw the graph, then it will be a straight line. And the value of electric field here will be sigma upon 2 epsilon naught. So this is the infinite charge non-conducting sheet. Now if we see two infinite sheets. Suppose this is the one sheet, charge density is sigma, and this is another sheet, charge density is sigma. Both are positively charged. So at this point, due to this sheet, electric field will be sigma upon 2 epsilon naught, and due to this sheet, sigma upon 2 epsilon naught in this direction. So it will be sigma upon epsilon naught. Similarly here also, in this direction, sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, so it will become sigma upon epsilon naught. But in between these two sheets, due to this sheet, electric field will be in this direction, and due to this sheet electric field will be in this direction and magnitude is same, so E will be 0, right? E will be 0. If both sheet have the same charge density, if they have different charge density, then we will put the values of different charge density, sigma A and sigma B. Here it will be sigma A upon 2 epsilon naught, and here will be sigma B upon 2 epsilon naught, right? Here it will not be 0, it will be sigma A minus sigma B upon 2 epsilon naught. Now the next, due to a hemispherical charged body, if the charge on this surface is sigma, then the electric field at center will be sigma upon 4 epsilon naught. Remember this formula. Now the most important, due to uniformly charged disk. So हमने सर्कुलर रिंग की वजह से देखा था, अब हम एक डिस्क की वजह से देखेंगे. सपोज द चार्ज इज Q over the charge density is sigma, then from the center of this disk electric field at this point P, which distance is r from center, radius is capital R. So जब हम इसको डेरिवेशन करते हैं तो बहुत सारे रिंग एज्यूम करके इसका डेरिवेशन किया जाता है, एंड द इलेक्ट्रिक फील्ड विल बी सिग्मा अपॉन 2 एप्सिलॉन नॉट 1 माइनस x अपॉन स्क्वायर रूट x स्क्वायर प्लस r स्क्वायर. व्हाट इज x? इस डिस्टेंस को r ने एज्यूम करके x एज्यूम कर लेते हैं. Similarly to rain. So this will be the electric field. Now at center, so for center put the x equals to 0. So at center x equals to 0 and it will become sigma upon 2 epsilon naught. So near the disk जो भी पॉइंट्स होंगे उनके लिए एक इन्फिनिटली सीट की तरह बिहेव करेगी, राइट? नाउ वी विल स्टडी अबाउट इलेक्ट्रिक फील्ड लाइंस. व्हाट आर द इलेक्ट्रिक फील्ड लाइंस एंड व्हाट आर द प्रॉपर्टीज ऑफ इलेक्ट्रिक फील्ड लाइंस. सो इलेक्ट्रिक फील्ड लाइंस, फर्स्ट ऑफ ऑल ये इमेजिनरी लाइंस होती है, लाइक कहीं पे कोई ड्रॉ की हुई लाइंस नहीं होती, इमेजिनरी लाइंस होती हैं, एंड दीज आर द ज्योमेट्रिकल रिप्रेजेंटेशन ऑफ द इलेक्ट्रिक फील्ड. देयर इज नो फिजिकल एग्जिस्टेंस ऑफ द इलेक्ट्रिक फील्ड लाइंस. सो एन इलेक्ट्रिक फील्ड लाइन इज ए कर्व which is drawn in such a way that tangent at a point, tangent at a point will show the direction of the electric field at that point. If we will here will draw a tangent, the electric field direction will be in this direction. If we draw a tangent at some another point on this curve, then the electric field direction will be like this, in direction of the tangent. So electric field line is a curve drawn in such a way that the tangent to it at each point is in the direction of the net field at that point, and the electric field line is a purely geometrical representation and has no physical existence. Now properties, first of all electric field lines from for a positive charge will be radially outward, like this. For a negative charge, radially inward. Right? So we can say electric field lines start from positive charge or infinite. If there is negative charge only, then we can assume that they are starting from infinite and end at negative charge or at infinite. So considering these two lines, we will draw electric field lines for some other bodies also. So considering these two properties, we will draw electric field lines for a pair of charges. Suppose both charges are positive charges. Then electric field will be like this, radially outward, and for this electric field lines will like this, but it cannot end here, so it will like this. For this also it will be like this. And there will be a point where the net electric field will be 0. In between these two charges, that will be the midpoint of this distance. There will be electric field will 0 because there is no electric field line. Similarly, we can draw for a positive charge and for a negative charge. So electric field will start from positive and will end at negative. In this direction also, it will be like curve. So we can draw the electric fields for positive charge, negative charge, for pair of charge also. So electric field line starts from a positive charge or infinite, and electric field lines end at the negative charge or the infinite. So these are the electric field lines for a positive and negative charge. Now the electric field lines never intersect each other. Why? First we will understand this. Why? Suppose there is a point P and one field line is in this direction and the other electric field line is in this direction. Now the electric field direction at point P will be tangent at the electric field line. So here will be tangent in this direction also. This is the tangent at this line, and there will be tangent also at this line also. So here the direction of the electric field at point P. So here are the two directions. One direction in this direction and one in this direction, which is not possible. So the electric field lines never intersect each other. The second is the electric field lines never form closed loop, but the magnetic line form the closed loop. We will see this in magnetic field lines. The magnitude of the field is represented by the density of field lines. That means the magnitude of electric field, it depends on the density of field lines, how much electric field lines are passing from a surface. That will be the directly proportional to the magnitude of the electric field. Or we can say, suppose there is a charge Q, that is positively charged Q, so electric field will be like this in this area if we see. So if we see here, then electric field lines from this surface are more than if we take similar surface away from the charge. Then there will be electric field lines passing from this surface will be less. So we can say that when we go away from the charge, the electric field gets weaker and the density of field lines are less. Or in other words, electric field is strong near the charge and the density of field lines is more near the charge, and line will be very closer. We can see here, near the charge electric field lines are closer and electric field will strong near the charge. So we can say electric field strength is directly proportional to the number of field lines, and this is also true. We can see by formula also, E equals to, for a point charge, KQ upon R square. So if R is very less, then E will be the very large, and if R, when R is increasing, then E will decrease also. So depending on this concept, we will solve a question. First we will see what is the uniform electric field and what is non-uniform electric field. So uniform electric field is represented by parallel lines, and that parallel line will be placed at same distance. Non-uniform field line, the whenever we will solve some question or will draw lines, then we will draw like this for non-uniform field. Field lines will be, can be curved lines also, and field at different distances. Suppose this distance is R1, then this distance will not be R1, this another distance, suppose R2. So if electric field lines are like this, then these electric field lines will be called non-uniform field. Now depending on that property, we will solve a question. Property was electric field strength will be proportional to number of field lines. So here we are given, consider the situation shown in figure below. What are the sign of Q1 and Q2? If the lines are in proportional to the charge, what is the ratio Q1 upon Q2 also? First of all हमें calculate करना है what are the signs of Q1 and Q2. So here we can see electric field lines are ending at Q1, that means Q1 is negative. That means Q1 is negative charge, and electric field lines are starting from Q2. That means Q1 is positive charge. Q2 is positive charge. Right. Now here it is given the if the lines are in proportional to the charge, that means lines, number of lines directly proportional to the charge, then the ratio Q1 by Q2. So number of lines originating from Q2 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 is proportional to Q2, and electric field lines ending at Q1 6. If we solve this, then Q1 by Q2 will be 6 by 18. So this will be the answer. Now we will see another question, and then we will see a property of the electric field lines. In this question we are given 3 electric field lines, right? And electric field at some points. Point A, electric field is EA, denoted by EA. Electric field line at B, denoted by EB, and at C is EC. Now we have to arrange the EA, EB, EC in a order. Now, where electric field lines are more, then magnitude of field will be more strong, right? So here we can see, if we take a area we take a small area, in this area 3 electric field lines are passing, and if we take this area, similar area here, then we can see only 1 electric field line passing through this area, and at C these 3 lines passes. So we can see definitely EA equals to EC, and EA is greater than EB, and EC also greater than EB. So correct answer will be, this is not correct, this is correct. So magnitude of the electric field is directly proportional to the density of electric field lines, and we have used this concept here. Now we'll check one property of the electric field. Electric field lines are always perpendicular to the conducting surface. If this is a conducting surface, and there is a conducting surface here also which is negatively charged, then the electric field lines will like this, will originate from here and will end here. If there is a charge Q plus Q charge, suppose this is a conducting sphere, then electric field lines are always perpendicular to this surface. And if there is a sheet of negative charge, which is a conducting surface, then these will end like this, perpendicular to the surface. In this direction, they will be perpendicular to this sphere, radially outward. So electric field lines always perpendicular to the conducting surface. Are always perpendicular to conducting surface. So in this chapter we have studied about electric field. So electric field due to a point charge and electric field due to a sphere, non-conducting sphere, conducting sphere, then non-conducting cylinder, then conducting cylinder, then a line charge, then infinite long line charge, and due to a ring, due to a circular disc. And then we have studied about the electric field lines and their properties. Now in next lecture we will study about the electric flux and Gauss law.